Hey folks, this is Merv Griffin, and this lesson is on other ways to measure your spread of your data. Okay, let's do the board problem. The mean salary of all female workers is $41,000. The mean salary of all male workers is $35,000. What must be true about the mean salary of all the workers described here? So it says it must be $38,000. Boy, that's the average of these two numbers. That's a trick right there. It must be larger than the median salary. Well, we don't know how many female workers there are. It could be one female worker and 10 male workers, or it could be one male worker and 10 female workers. So since we don't know how many females and how many male workers we are, the only thing I can verify is it's going to be any number that's going to be between 35,000 and 41,000. I don't know any of this because any of the others right there because I just don't know how many workers are in each gender. Okay, all right, so here's section 1.21, other ways to measure spread, and we're going to talk about variance. Variance, which is S squared of a set of data, and this is x sub 1, x sub 2, x sub 3, all the way up to x sub n. You know, like we did the Hank Aaron's and Barry Bonds home runs. Those home runs would have been the x sub 1, x sub 2s and stuff. Okay, so they're just the numeric data. Okay, now the variance is this. Now x bar, these x bars are the mean. So what I'm going to have to first do is find the mean of these numbers, add them all up and divide by the number of numbers. And then I take each number minus the mean squared, plus the next number minus the mean squared, plus the next number minus the mean squared. And you add them all up after you squared them, and then divide that by n minus 1. Okay, and then that's what's called your variance. Okay, and it's just another way to measure how much the numbers vary by. That's where variance comes by. A larger variance means the numbers vary more, which means the numbers are more spread out. The smaller the variance, the more closer theirs are. So like, for example, my AP statistics students, if I said, you know, calculate the variance of their GPA, it would be a small variance because they're all pretty much tunneled up into the AP stats class. You know, if I said calculate the variance of, say I was teaching a math 7, I had some really sharp kids and I had some kids that really struggled with math, and the variance of those kids would have been quite large. Anyways, you guys, so here's my n minus 1. It's 1 over n minus 1. And you remember this from Algebra 2? This just says the sum of I equal 1 to n. Here's my I equals 1 right here. Here's my I equals n, and here's all the ones in between them squared. So that's the shortcut formula right there, okay? All right, and then standard deviation, that's the number that we really focus on, is just the square root of your variance, okay? And so standard deviation is just another form to measure spread. Okay, some calculators give you an option to divide by n or n minus 1. We always choose n minus 1, and I don't know why, but that's okay. We just choose n minus 1, okay? All right, so I've taught out of an Algebra 2 book. They just chose n. Okay, metabolic rate. This is example 1.14 on pages 49 and 50. I'd like you to write that down if you're in my class, but not this. Just listen as I read. A person's metabolic rate is the rate at which the body consumes energy. Metabolic rate is important in studies of weight gain, dieting, and exercising. Here are the metabolic rates of 7 men who took part in a study of dieting. The units are calories per 24 hours. Okay, so these are all calories here per 24 hours. These are the same calories used to describe energy contents of food. Okay, so first thing I'm going to do is have to add all these numbers up and divide by 7 because there's 7 numbers. I need to find the mean. Okay, so here we go. Okay, so here they are all up, divided by 7, and you get 1,600 calories. That's the average of all those guys. So then I'm going to do 1792 minus 1,600 squared, plus this number minus 1,600 squared, plus this number minus 1,600 squared, plus dot, 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 plus this number minus 1,600 squared. And then divide that by what? 6, because it's 7 minus 1. Alrighty, so they did that in kind of a different way. I wouldn't have done it this way. I would have kept doing it like I showed you on that formula. So here's the first number minus 1,600, and then so it's that. Then they squared it right here, and so there's that. Okay, and here's the next number. Subtract 1,600. So here's all the numbers minus 1,600, and here they all are squared, and then here's the sum of them. So then they added them up and divided by 6. So that's the variance right there. Remember, the variance is x squared. So the standard deviation is the square root of that, so it's 189.24. Okay? So this next figure shows the 7 points. You don't have to write this down if you're in my class. Purple, you usually don't have to write down, just in case you wondered. Shows the 7 points above a number line along with the mean marked with an asterisk. Okay, the arrows, let me just show you here. The arrows show, so here's all the 7 numbers here. Okay, here's all these 7 numbers, these little dots right here. And here's the mean with the asterisks right there. Okay, and the arrows are showing 2 of the deviations from the mean. So here was one of them right here. Its deviation from the mean was negative 161. I think it was, let me go back, the negative 161. That was this one right here. So the 1439 minus 1600. And then the other one is 192. So its standard deviation was, its deviation, it deviated from the mean 192. Okay? So the sum of these deviations observed in their means will always be 0. Okay, the variance is larger when the more spread out the numbers are. So all these variances, when I add them together right here, you guys, they always add to 0 right there. But when I square these numbers, square numbers are always positive. So when I square them, I get a big old number, and I divide it by n minus 1 to get the variance, and then square root that stuff. All right. So properties of your standard deviation. Okay. Standard deviation is x. You use S, that's what standard deviation is. You use standard deviation only when the mean is chosen as the measure of center, not the median, not the mode, only the mean. And like the mean, standard deviation is not resistant to outliers. So if we had some Bill Gates living in the neighborhood, it would affect your standard deviation a lot. Okay, strong skewness or few outliers can make S very strong. I'm sorry, S very large, I'm sorry. So for example, in varied bonds, the lesson we did prior to this, the standard deviation was 13.633. And when you took out that outlier right there, the 73, look, it made the standard deviation much smaller, which they just mean the numbers vary less when you take out the outliers right there. So strong skewness can make your S larger. If the distribution is strongly skewed or has strong outliers, then the 5-number summary system is a better system to use than to do the standard deviation. Here's my 5-number summary system, okay, spoken about in the last lesson. All right, so let's do bonds in the calculator, you guys, all right? So let's go ahead and do that. So here's his numbers right there. Put that in list 1, or if you already have it in list 2, you can go ahead and just do list 2, you guys. And then you're going to do, I put it in list 1. But if you did it in list 2, then you do stat and then scroll over to calculate, 1 variable statistics, and then pull it out of list 1 or list 2 if you did that. And if you hit enter, you should get the 13.633. All right, it's that it says x, or so it says S of x. It's the standard deviation of x. So you see that in your calculator. And then what you can do is go back to your list, you guys, your list 1 or list 2, whichever one it's in, and just delete out that 73 and then go through this again. And then you'll see the standard deviation gets a lot smaller. All right, so the calculators are a great tool. Okay, so changing all the data by, if you multiply all the numbers, say I multiplied all those numbers by C, then that's going to multiply both centers, so your mean and your median, by C, so everything gets multiplied by C. Both spreads, so your standard deviation and your IQR by C, so everything gets multiplied by C when you multiply each observation by C. However, when you add all observations, I should have wrote by C, but I wrote by Y, it doesn't matter. Then you add the centers. You add the center is going to be plus y and the quartiles are going to be plus y, but it won't change your spreads. It won't change your range or your IQR. It stays the same. The spread stays the same when you add, but when you multiply, everything gets multiplied. Alrighty, so this is just a real quickie, you guys. Dual graphs. So you're going to do dual graphs using some cool car colors in example 1.16 on page 57. Okay, so you have these cool car colors on cars. Boy, that was a tough one. So we have full size and intermediate size, and then we have light trucks or vans. Okay, we have medium or dark. So I'm going to make some histograms, but they're going to be dual graphs on here, and I'm going to show you right here. Okay, can you see the dual graphs? Here's the lighter graph, and here's the key right here is the full size or intermediate size car, and the darker graph is the light truck or vans. Okay, so that's how you do a dual graph of a bar graph right there, just right next to each other. Here's my medium or dark green. Here's my white, my light brown. So my light brown, say for here's my light brown, it went up to 14%, and then it went to 6.1%. So here's my 14%. Here's my 6.1%. Okay, 14.1%. Alrighty, okay. And then if you're in my class, I'll tell you about the homework assignment tomorrow. Take care.